All right, so let's talk about a couple things I just want to get to today. So first one that's real important. Go ahead and click them all the way closed and get your attention up here. So is differentiability of functions, right? So first of all, what does differentiability even mean? You could define the word differentiability as this. It's take the derivative ability, right? So a derivative, let's kind of get the vocabulary straight here so you don't sound like a doofus when you go to college and you're talking about calculus. A lot of times people say, like, they talk about the derivative is the noun, right? If we're taking a derivative in calculus, we are developing the function called the derivative function that stems from the original function, right? And so far we're doing this the long way with limits right now. But if derivative is a noun, what's the verb that goes with that, right? To do that process, contrary to what you might think, it's not derive. And people oftentimes want to say, I'm going to derive the derivative. That's not, it seems like it ought to be, but it's not. The verb is differentiate. And we'd say that this whole first half of the class is called differential calculus because it's the calculus related to differentiating functions, right? So then differentiability is the adjective we give to a function to say, yes, we can take the derivative of that function. Where it's differentiable are all the values of x where I can differentiate the function. Does that all make sense? Just kind of a stew of vocabulary there, but you'll just contextually, you'll get all this because that's one of the things that I think is really valuable in a math class is just to be able to, I'm just going to model how you say this stuff correctly, and just like little kids learn how to speak a foreign language, and they learn proper syntax and grammar from listening to adults, right? Same thing with math. So the first thing we're going to talk about is differentiability. So where are functions differentiable? Well, really, functions are differentiable every place except the places where they're not differentiable, right? So really what we want to focus on here is where are functions not differentiable. Just like we talked about, we talked about the continuity of a function, really we want to just specify, we want to find the places where it's not continuous, and every place else it works, right? So what are the types of places where functions are not differentiable? There's a short list of places that we got to know about. So functions fail to be differentiable. Derivatives don't exist where, first of all, there are discontinuities in a function. Okay? So any place where a function is not continuous, the derivative absolutely can't exist. Okay? It's impossible. And why is that? Well, I'm not going to try to attach a bunch of mathematical rigor to this, but we can sort of finesse our way through maybe a connection here. Continuity relies on, think about, let's go back, this is good review, and it's helpful to kind of put all these pieces together. When you make these connections, that's when math really starts to feel like it's solid. Continuity at a point requires what three things? What are the three criteria for a function to be continuous at some point? The function's defined there, first one. The limit exists there, and then the last one, the limit equals the functional value, right? So the value of the function and the limit agree, okay? Well, so continuity depends implicitly on then being able to take a limit, right? The limit has to exist. And so, why wouldn't that work for a derivative? Well, when we're calculating the derivatives, all the stuff we spent time on yesterday, and I think even the day before, right? So the last couple days, that limit process, or the process of finding the derivative of a function depended on limits, right? So someplace where a limit doesn't exist, doesn't it stand to reason then that the whole derivative process is going to fall apart if the limit doesn't work, right? And so there's a way to make that connection, right? The places where the function is discontinuous, obviously we can't calculate a derivative, okay? Corners. Okay, now this is, and we'll go through, we'll kind of talk about why this is, but for now we'll just look at the list. Points where a function is continuous, but the derivative from the left is not equal to the derivative from the right. Okay, and we'll talk about that in much more detail here today. But that's another kind of a place. And we'll look at examples of all these types of places. Vertical tangents. Okay, now why might that be the case? Vertical tangents are going to be places where the derivative has the slope of the function would have a value of what? If it's a vertical line. What's the slope of a vertical line? Undefined, right. And why do you suppose it's undefined? I mean, if you think about slope as a rise over a run, what value would the slope be approaching there as the rise becomes really big for any small run? Infinity, right? Okay, so effectively, what's going on there is when you have a vertical tangent, the slope is undefined because its value is approaching infinity, right? Okay, and along with that, kind of a subtext for vertical tangents would be cusps. Cusps are sort of a combination of corners and vertical tangents. Okay, it's a place where you get infinitely sharp corners where the derivative from the left and the right approach opposite infinities. And that's, we'll look at an example of that. Okay, so a couple things then. So we said differentiability is the ability to take a derivative. This next statement is a huge one in calculus. You got to remember this. So tattoo that one in your brain. Differentiability implies continuity. Take a second and somebody see if you can explain to everybody here, articulate, what does that really mean? That's a really important statement. It's a one-way statement. So differentiability implies continuity. Let's see if this makes sense. So if a function is differentiable, then it's necessarily continuous. Has to be, right? And we said that up there.
Yes.
If it's not continuous, it is not differentiable, right? But can you assume that just because a function is continuous, it's differentiable? No, you can't, right? So differentiability implies continuity, but the inverse is not true, right? If we read that statement backwards, it's not true. And an example would be a corner. Okay, a corner is a place where the function is continuous, but the derivative is still not defined, okay? So let's look at examples of these. So what about a discontinuity? And we'll just take, for this, we'll just take our greatest integer function, step function. Okay, something like that. Now, why, well, let's take at x equals 2, for example. Okay. Why does that not work? It seems like there's an argument where you could say, well, the function seems to have the same slope on the left as it has on the right as it approaches that value. Okay, but because there's a break in the function, and the function, yeah, the limit falls apart there. Okay, does that make sense? Here's another way to think about that. Where, if we attach solid and open endpoints to this is a function, right? So it has to pass the vertical line test. Where would I put, when I get to 2, what is f of 2 for this function? It's 2, isn't it? So that's got to be a closed endpoint. This has got to be an open endpoint, right? F of 1.999999999 is 1, right? But f of 2 is 2, okay? So if we're trying to figure out what the slope is as we approach a value here, when we do our, if we're trying to calculate the derivative, say from the left and the right, remind me real quick, what's our definition of a derivative? Like if I want to calculate, if this is f of x, what's f prime of x equal to? The limit of f of x
minus
plus
H.
delta x, I'll call it h. So I have limited room here. Minus f of x divided by h as h approaches 0, right? Okay, so now what if we apply that, we're going to do a limit from the right here instead. So what if we're approaching 0 from positive values? right? So what's that mean? Essentially, we're taking a derivative from the right then, aren't we?
Yeah.
Does that make sense? We could say, derivative from the right would be f prime of x equals the limit of f of x plus h minus f of x as x approaches, or sorry, as h approaches 0 from positive values. Agreed? Okay. So what's going to happen there then? We're going to be taking values like, if this is h, when we're approaching from the right, as the ant walks towards this value, he's going to see a slope of 0, correct? But what about an ant walking from the other side? He's not going to end up seeing a slope of 0 because he's comparing his current spot to this point right there. That is, does that make sense?
Yeah.
Right? And so he's going to see a different slope on the left than the guy on the right is. See what I'm saying? They don't agree. Okay? How about if we take something, the same thing would happen, you know, like down here we can see the same type of thing happening. As I approach 0 from the left, and this one's clearly different, right? Because this time on the left side, as an ant walks down this, he's walking down a line that clearly has a different slope than what he's anticipating as he gets to the bottom here, right? So we know if there's a break in the function, all bets are off, right? It's not differentiable. Okay, what about something that's a little more subtle, like a corner, like the absolute value of x? And we don't even really probably have to be too sophisticated with this. We could just look at this function and just, let's say our ants now, our calculus ants, you know, they've got this ability to sense their position on the function, which we took advantage of when we talked about limits, right? So they're, what coordinates do they anticipate stepping on when x approaches a certain value correlates to our definition of a limit from earlier in the year. Remember that stuff? They've evolved a little bit, and now they have built-in slope sensors too. So they can sense as they walk along a function, they sense the slope of the function that they're walking on, the slope of the tangent to the curve. These are pretty highly evolved ants. So ants that are walking along the function approaching 0 from the left and from the right, they both anticipate stepping on the same place because the function is continuous there, right? Okay. The limit exists, doesn't it, in this case? What do their slope sensors say, though? The ant approaching from the left anticipates a slope of what?
Negative x.
Negative 1 in this case. The ant approaching 0 from the right, his slope sensor is anticipating as he steps on 0 a slope of what? Positive 1. Okay? Well, which one is it then? If the ants are both approaching the same point from opposite directions, which one should be correct? Should there be a preference? Should it matter which direction you approach 0 from? Shouldn't make any difference, right? There can't be, mathematically, that would make no sense that there would be some preference for this side or that side. It makes no sense. I mean, this two-dimensional space ought to be isotropic. There shouldn't be any, there can't be any preferred directionality here. It just makes, because it's all arbitrary, right? Why do we call this the positive direction, but why? I mean, that's just sort of a human convention we imposed on this whole idea, right? So doesn't it make sense that you can't have a preference, and so the slope can't exist? There can't be a slope at that point because you're getting different values as you approach from different directions, and slope depends on a relationship between 2 points, right? The whole concept of a slope is the relationship between a point and another point, right? So you can't define a slope in a sense. You can't really define a slope for an isolated point. At that isolated point, the slope depends on the relationship of that point to its neighbors on the left and the right. Does that make sense? So because we can't agree, you can get different values from the left and the right, you can't define a slope there, therefore that's what derivative means. The derivative is not defined. Okay, make sense? Now, we could say a derivative from the left or a derivative from the right. The derivative from the left is defined. It's -1. The derivative from the right is +1. But because they don't agree, the derivative doesn't exist. Okay. And then same kind of thing there, right? We have this piecewise function, and from the left, we have a slope of -4. The ant senses a slope of -4. From the right, he's sensing a slope of 0 as he approaches that point, and they don't agree. Could you have a piecewise function that would knit together in a way where the derivative would be defined? What do you think? Like, how could I change this part of the function, this piece of the function right here, to turn this into a function that is differentiable at 0? What would its slope need to be? I mean, it could be an infinite number of different functions, but the slope from the left has to be what? If it's going to knit up with the slope from the right. Yeah. Well, what's the slope from the right? 0, right? So the slope from the left would have to be 0 also. So you'd have to just pick a function for which that is true. You know, it could be an easy function. Like we could just replace this with f of x equals 0 when x is less than 0. And what would that look like? That would just look like a horizontal line. And that would work. In this case, the red function would get a closed circle at the end point, and the blue function would get an open end point, but they match up, and the slopes match up from the left and the right. And so that actually is a piecewise function, but it would be differentiable. Make sense? Okay, we could just as easily do something like, we could say maybe instead negative x squared when x is less than 0, and then that would just look like that. But the slopes still match up. So it would be differentiable at that point. Yeah, does that make sense? Mm-hmm. Okay. There we go. So vertical tangents. We get a vertical tangent for this function, for example. Let's demonstrate that. Let's demonstrate that that's the case. Let's just show this using, we'll get a little practicing from yesterday. We've got to reinforce what we did yesterday. So let's calculate the derivative of this function at x equals 0. Okay? So start at the start. Start general. What's our definition of the derivative?
X.
What's f prime of x?
Limit
The limit of
f of x plus h minus f of x all divided by h. As h approaches 0.
Okay, good. So there's our function is x to the 1/3, so now let's make this specific. So this becomes what's that going to be? What's f of x plus h? If f of x is x to the 1/3. So it's going to be x plus h to the 1/3 minus x to the 1/3, everybody agree? Divided by h. Well, this is going to be a tough one. How are we going to do that? We do limits. That's going to be a pretty hard one. We're going to have to multiply by a pretty wicked. We're not going to take time to do that. You'd have to, that's going to be pretty hard to do. It's just so you see why I'm neglecting this one. How do I factor a cubed minus b cubed? Remember that's a minus b times squared, not plus. AB plus
B squared.
B squared, right? So what would we have to do to apply that here? We'd have to do something really tricky, like we'd have to say, okay, well, if that's true, then we could say that A minus B is equal to A to the 1/3 minus B to the 1/3 times A to the 2/3 plus A to the 1/3 times B. That's gonna get really nasty, isn't it? We don't wanna do that. We don't wanna go there. That's gonna be a tough one. But we don't really probably need to do that anyway. You can see here that as we approach, for now, this is gonna be fun. As we approach, as we pick these tangent lines, and this is a good way to think about this, the slope of a function, remember, is really defined by the slope of the tangent to the curve at that point. So we'd have, like, at this point right here, because the tangent line looks like that, that's the slope of the function at that value of x. Up here, the tangent gets steeper, and so the function has a steeper slope. Steeper yet, in the middle, we're approaching a value here where the function is infinitely steep, right? And so at that point, we can't define a slope. Because the slope is undefined, the derivative doesn't exist, because the derivative is what gives us the slope, right? And then up here, it starts to level out again. So the slopes decrease in value, and so the value of the derivative decreases. So we'll look at some examples. Today, at the end of the day, that's the last thing we'll look at is, can we just take a function, a picture of a function, and sketch what its derivative looks like based on the relationship between function and its slope, right? That's a good skill to have, especially for physics. And then the last one are cusps. And the last of the topics or the last of the category of places where functions don't exist would be a cusp. Here's an example of a cusp. You see what I mean by it's a hybrid of a corner and a vertical tangent, right? This is a place where the function, as we approach from the left, the slope sensor is going crazy. It's saying a value of negative infinity, right? As the ant steps towards a value of 0, he's anticipating stepping on the point 0, 0, but he's anticipating a slope of negative infinity as he steps there, right? How about approaching from the right? Well, the ant's anticipating stepping on the same point. The function is continuous there, right? But what does he anticipate his slope to be? Well, negative infinity, okay? And so we get this infinite difference. And so once again, the slopes don't align, and so we can't define a slope there, okay? All right, so those are the places where it doesn't exist. Now, here's my challenge to you. Now I'm going to give you a function, and I want you to define for me what the derivative looks like, okay, for this function. So here's the function. Our function is just going to be, we'll start easy here. So that's F. What's F prime look like? Now, how are we going to come up with this? What's the relationship between the derivative function and the function? The derivative represents what again? The slope, okay? So the value, now listen carefully to this statement. It's a simple statement, but you gotta really make this connection. The value of the derivative corresponds to the slope of the function at that point, right? So if I want to find the value of the derivative function at that point, what's the slope there? 0. Okay, so then this point right here is going to map to a slope value there. In fact, does it ever change? Okay, so the derivative function looks like that. See my point? Okay, let's do another one. So how about if we do this? That's, I'll call it y this time. So what's y prime going to be? At some positive, I didn't put any increments on the graph, but would you agree it's some positive constant?
Yes.
Right? So that's y prime. Okay. How about this?
positive line.
Okay, so
This is flat.
in fact, assuming these are parallel line segments?
Yeah, it'd be in the same spot.
How come?
Because the slope is
Slope's
the
the
same.
same, right. So there's something interesting. Does the value of the derivative depend on the value of the function? No impact at all, right? It only depends on the slope of the function, right? Okay? So later in the year, and this is gonna be a little disjointed right now, but you're gonna remember this when we come back to this in about 4 months. If I were trying to reverse this process, if I were given the derivative function, and I were trying to go backwards and figure out the function from which the derivative came, well, is there one answer? No. I could get this answer, or that answer, or an infinite number of other possibilities that are just offset vertically, and they'd all be correct. Everybody see that?
Yeah.
Okay, so we'll discuss that later, but you get the idea. Okay, let's keep going. So obviously, what's gonna happen then if I do something like that? Negative constant, right?
Yeah,
Because the
yeah.
slope is a negative constant. Okay, good. So you guys you're getting this. This is good. Okay, now let's get a little trickier. Now let's do something like that. And let's assume that the slope of the line is increasing uniformly. Okay. So what's happening here? Now this time, we got to maybe take some individual points and map those to derivatives. So like what slope is the ant sensing right there? 0, okay. So that goes there. What slope is the ant sensing right there? Some positive number, right? Because it's, okay, so we'll just say hypothetically that right there, then it's gonna be some slope right there. How about up here? A more positive integer. So if we're saying that the slope is increasing uniformly, what kind of a relationship should I probably have here? Does that make sense? The slope is increasing at a constant rate here as we move from left to right. You see that? Okay? So this is y, and that's y prime. Okay, good. How about this one? Thank you. Okay, so now this one takes a little more thought. Maybe we want to try to anchor this. We can't do an exact graph because we don't know we don't have numbers, right? This is not a graph paper, so we can't make a really accurate guess about any of the exact slopes, except one of them. There's one slope on that red function that we know exactly what it is. Okay, yeah, what's going on? Cody, what's happening right there? What's the slope of the curve right there?
Would be undefined.
Not undefined. Well, the tangent looks like this, right? So a horizontal line has a slope of what?
0.
0, right? Okay, so we can see that at the point on the curve where the tangent is horizontal, and this is a huge deal in calculus, that's a place where we know the derivative has a 0. Okay? And then to the left of that, what's going on? The function is increasingly,
Getting closer to infinity.
okay, right, but it's increasingly positive.
Yeah.
Yeah, and this one never quite gets infinite, but that's going to be a place, like if I go out here to the very end, that's going to be a place where we get some positive value. How about over here on the right?
You're going to get to the negative.
Some negative value. Okay, and then that's our graph, isn't it? You know what I'm saying?
Yeah.
Okay. Okay, now, These are just random mathematical graphs, but let's change these around. Let's say here that y represents position, and what'd you tell me yesterday the derivative of, or the rate of change of position defines what function? Velocity, right? And so the instantaneous, if we look at the slope of the tangent line, it's not an average velocity, it's an instantaneous velocity, right? So there's our relationship in calculus, just from yesterday. If x of t equals position, in this case, x prime of t equals instantaneous velocity. So in calculus, you wouldn't even specify instantaneous. We just know, we assume if we're saying velocity, we're talking about a velocity function where we get an instantaneous velocity function, okay? So these tell more interesting stories then if we think about them in a kinematic context. Like what is this one saying? If this is the position function, it's saying I have some positive position that stays the same. So if this is 0, this isn't a very fascinating story. Start the stopwatch, stop the stopwatch. I didn't do anything, right? What's my velocity? 0. I didn't go anywhere, right? What about this one? It says I'm starting at 0, and I'm walking, so I'm increasing my position at a constant rate.
Yeah.
So I'm just doing this. Stop the stopwatch. Not very exciting. That's just a positive constant velocity, right? What's this one? Well, same thing, only I'm starting at some negative position. Start the stopwatch. Stop the stopwatch when I get to 0, right? Still, positive constant velocity. How about this one? I start at some positive position, start the stopwatch, I'm becoming more negative, stop. I stop at some negative position, right? What did I do? I just had some constant negative velocity the whole time because I'm moving in the negative direction, right? How about this one? Now I'll get a little more interesting. I'm starting at position 0, and I'm starting at rest, start the stopwatch, and I'm accelerating, stop the stopwatch, right? So I started with 0 velocity, and I increased my velocity at a constant rate. So I had, in other words, describe my acceleration there, physics times, if you're in physics. I had constant positive acceleration, right? Does that make sense? Okay. Could you make a link here? Okay. Now I'm kind of jumping ahead just a tiny bit, but it's all right. I mean, we'll get back to this idea. So if we define V as x dot, or excuse me, x prime, we'll call it. The dots we'll get to that later. Dots are special derivatives, but we don't want to confuse things. The derivative of position is velocity. What do you suppose acceleration is defined as? What do you think? Now, you just told me, this makes sense, right? If you've studied kinematics at all, even if you haven't, this isn't a really, you'll get this, right? Velocity is the rate of change of position, okay? Acceleration is
The rate of change of velocity.
the rate of change of velocity, right? So we could even define something like, we could say A for acceleration, A of t equals V prime of t, okay? Now, hold on to your head, don't just do this so your head's going to explode. If acceleration is the derivative of velocity, then it's what we call the second derivative of position. The derivative of the derivative is what a second derivative is. Okay? So we could graph that also. That's a pretty boring thing to do for all these early drawings up here, because in each case, like in this case, the velocity function is 0. But what's the derivative of 0? It's 0, right? How about here? Well, what's the derivative? If I want to put a second derivative up here, what's the slope of that blue line?
0.
So I'm just going to have something like that for my second derivative. Same thing here, right?
Yep.
the derivative of the blue function is 0. Okay, but what about here? So derivative of the blue function here, it's a positive constant slope, isn't it?
Yeah.
So I'm going to get something like that for my second derivative. That's consistent with our story, right? You told me that, or you nodded your heads when I said this, that that's a positive constant acceleration if I'm starting at rest and I'm increasing my speed at a constant rate. That's what acceleration means, right? Oh, wish we had more classes. Okay, what about this one? Okay, that's a negative constant, right? So let's look at this story then. This story says I'm starting here. We start the camera, I'm moving pretty fast in the positive direction, right? I've got pretty high positive velocity. So but I'm slowing down, I'm in rest, and then I'm speeding up in the negative direction, right? Okay, so that's negative acceleration. Here's something that'll be helpful. If you want to think about acceleration, you guys have talked about how acceleration is related to force, probably, right?
Yeah.
Proportional F equals ma. So when you talk about acceleration, think about it in terms of an invisible hand, right? So if this is the story I'm telling, I'm starting fast and I'm slowing down and I'm increasing my speed in this direction. In which direction is the invisible hand pushing me the whole time? It's pushing me this way, right? At first it's removing my velocity and then it's adding to my negative velocity, right? So that makes sense then. That correlates to a negative constant acceleration, right? Get the idea? Okay, we'll pick this up Monday. Tomorrow you guys will be able to retest if you want to, or just work on assignments, okay? I'll be gone.